So at first, this is a short summary about the experiment 6 that is about torsion of bar. So in this experiment, it's the aim to understand the behavior of the material under the twisting load by applying the torque or twisting moment to a cylindrical or plasmic bar and observing its response. Hence, the objective of this experiment is to investigate the relationship between the torque T and the angle of twist of a circular cross-section specimen. So at the end of the experiment, we are able to prove that the torque is directly proportional to the angle of twist. The angle of twist is also proportional to the length of the shaft L. Based on the result calculations, the modulus of rigidity G also be able to calculate for the different material of the bar. So the modulus of the rigidity G that we obtained in this experiment for steel is 340.915 Newton over millimeter square. So the aluminum is about 300.378 Newton over millimeter square, and the iron is about 16.622 Newton over millimeter square.
For the introduction of this experiment, torsion is analyzed through the stress and strains in members of a circular cross-section subjected to twisting couples or torque. These couples have a common magnitude and opposite senses. They are vector quantities and can be represented either by curved arrows as shown in figure below or by couple vectors. Members in torsion are encountered in many engineering applications. The most common application is provided by transmission shafts, which are used to transmit power from one point to another. For example, a shaft is used to transmit power from the engine to the rear or wheels of an automobile. These shafts can be either solid or hollow. Next, for the objective of this experiment, it is to investigate the relationship between torque and the angle of twist of a circular cross-section specimen in the terms of the formula angle of twist equals to torque times length of rod divided by modulus of rigidity of material times with polar inertia moment. Next, for the theory, the angle of twist of a shaft is proportional to the applied torque and to the shaft length. When subjected to torsion, every cross-section of a circular shaft remains plane and undistorted because the circular shaft is axisymmetric. Cross-section of one non-circular shaft are distorted when subjected to torsion. Then from the figure that's been shown, we can see the shear strain or the distortion of the shaft. This is by considering a solid circular shaft of radius r and length L subjected to a torque at one end and the other end being fixed. Under the action of this torque, radial line at the free end of the shaft twists through an angle. Point A moves to B and AB subtends an angle at the fixed end.
So in this experiment, the apparatus that we used were the different weight of rods, a ruler, a spanner, a digital calculator's torsion bar stating machines, and 3 different materials of rods. There is aluminum alloy rods, steel rod, and nylon rod. So the next one is the methodology of this experiment. The first step are the diameter of the aluminum alloy rod is recorded. The second step are the rod is in position clamp and then put the loop hanger on the core. The third step are the rotation scale is set to 400 mm from the fixed clamp and the pointer put to 0 degree. The fourth step are the load by 10 Newton increment added until you reach 16 Newton. The fifth step are the twist of the specimens by reading the degrees at the pointer recorded. The sixth step are the roots was removed and then the rotation scales and the pointer 200 mm is set from the fixed clamp. The seventh step are the step 4 and step 5 repeated for this length. The next step is the root change to the steel root and the step 2 until 7 is repeated. The next step are the root change to the nylon rod and the above steps. By this time, the root was added in increment of 1 Newton until it reached 6 Newton. The last step are the angle of switch of 0 Newton of load is taken after all the roots are removed.
I will present part 6.1 result for this experiment. For table 1 shows the data for steel solid bar. The diameter for steel solid bar is 17.9 mm. When the weight of load increased, the torque at 200 mm and 400 mm twist increased. The twist of steel rod at 200 mm and 400 mm increased. For table 2 shows the data for aluminium solid bar. The diameter for aluminium solid bar is 20.9 mm. When the weight of load increased, the torque at 200 mm and 400 mm twist increase. In the result, the twist of aluminium rod at 200 mm and 400 mm increase. While Table 3 shows the data for nylon solid bar. The diameter for nylon solid bar is 32.5 mm. When the weight of load torque at 200 mm and 400 mm twist increase, so the result for the twist of nylon rod at 200 mm and 400 mm increase also.
Six point two discussion will be discussing the following items. Firstly, to what extent does the experiment verify the torque or twist formula based on the graph plotted? Based on the theory of the experiment, where the formula of the angle of twist, phi, is equal to TL over JG, where T equals to torque exerted on the shaft in Newton millimeters, L equals to the length of shaft in millimeters, J is the polar moment of inertia, which have the formula pi c to the power of 4 over 2 in the unit millimeter to the power of 4, and G is the shear modulus of rigidity in Newton per millimeter square. From the graph of the angle of twist against torque, we can modify the equation with the mathematical method, that is y equals to mx plus c, as y is equivalent to the angle of twist and x equivalent to the torque exerted on the shaft. And we know that the slope of the graph, denoted by m, is equals to L over jg, the length divided by the polar moment of inertia and the shear modulus of rigidity. Based on the graph plotted, it is known that although the calculation has the same shape of graph compared with the theory, it does have a different value of equation where the value of gradient m and y-interception c will be different. Also, although it shares the same formula, the value of the gradient is affected by the length of the shaft and also the diameter of the shaft. As in this experiment, the value calculated is only 400 millimeters and 200 millimeters. As a result, the experimental value may differ from the theoretical value. Secondly, we'll be discussing about the comparison between three different types of bars with different lengths of rotation scale and pointer from the fixed clamp. According to the data tabulated in Table 1, 2, and 3, when the length of the rotation scale and pointer from the fixed clamp is 200 millimeters, there is no angle of twist for the steel bar. The increment in the angle of twist when the load increases for the aluminum bar is less obvious compared to the nylon bar. The angle of twist for the nylon bar, when subjected to the same amount of load, is larger than the aluminum bar. When the length of the rotation scale and pointer from the fixed clamp is at 400 millimeters, all types of bars used in the experiment show the result of having an angle of twist when subjected to a certain amount of load. For each steel bar, aluminum bar, and nylon bar, as the amount of load increases, the angle of twist will also increase. The increment in the angle of twist with the same increment in load supplied is most obvious for the nylon bar, followed by the steel bar, and finally the aluminum bar. From the results, it can be said that the rigidity of the bar increases from nylon bar, aluminum bar, and finally steel bar. Thirdly, based on our findings, we'll be explaining the relationship between the modulus of rigidity of materials with the parameters such as types of materials for the bar, length of the bar, shape of the bar, as well as the polar moment of inertia. Based on the results of the experiment, it can be said that the modulus of rigidity of material depends on the type of material. The value of the modulus of rigidity, capital G, is higher when the material is rigid and more resistant to its shear deformation. The low value of shear modulus of rigidity indicates that the material is soft or flexible with only little force required to cause deformation. If we compare steel and aluminum metal, steel is much more durable than aluminum due to the higher concentration of carbon in steel. Therefore, steel is more likely to resist deformation or bend than aluminum. The value of G for steel bars will be higher than for aluminum. Nylon is a nonmetal and it is a type of polymer which makes it less stiff and less rigid compared to both steel and aluminum. Therefore, the value of modulus of rigidity for nylon is the lowest among these three materials. The shape of the bar will affect the value of rigidity modulus with a circular cross-section including hollow and solid cross-sections. We will have higher resistance towards the shear deformation if compared to other shapes of the bar such as rectangular and triangular cross-sections. Therefore, the value of modulus of rigidity for the bar with a circular cross-section will be higher than that of other shapes of the bar. The relationship between the value of modulus of rigidity with the length of the bar and the polar moment of inertia can be observed through the equation G equals to TL over J phi. According to the equation, when the length of the bar increases, the value of rigidity modulus obtained will increase. As the value of the polar moment of inertia increases, the value of rigidity modulus obtained will decrease. This indicates that if the dimensions of the bar increase, the value of rigidity modulus will increase, and the bar will be more resistant to shear deformation.
Conclusion for the experiment. We can conclude that the objective of the experiment has been achieved as the relationship between torque and the angle of twist of a circular cross-section specimen or material and the length of shaft is obtained. It is proved that the torque is directly proportional to angle of the twist. The angle of twist is also proportional to the length of the shaft, as shown in the formula below. From the experiment, the modulus of rigidity obtained for steel is 365.16 Newton per millimeter squared. Aluminium is 202.77 Newton per millimeter squared, and nylon is 14.24. The value of modulus of rigidity is higher when the material is rigid and more resistant toward the shear deformation. The low value of G indicates that the material is soft or flexible with only a little force required to cause deformation. Thank you.
8.0 Safety Procedure. One of the safety procedure for this experiment is personal protective equipment (PPE) to ensure all are wearing appropriate PPE, including leg cord and closed-toed shoes. Next, there are three types of solid bar: steel, aluminum, and nylon used in this experiment and must handle with care to prevent injuries. Wearing gloves can provide additional protection as this bar may have sharp edge. Moreover, to avoid sudden or excessive loading which could lead to unexpected torsional force, apply and distribute load on the hanger cord carefully. Besides, handling the load with both hands is very important to reduce the risk of drop, damage, and injuries. Furthermore, use calibrated tools like digital calipers to measure the diameter of the bars to get the more accurate measurement. Last but not least, ensure the solid bar are securely clamped in place as loose clamping will cause instability and compromise the result.